Okay, so now we are ready to talk about the angular momentum of a rigid body. Okay, so not just simple particles now, but a rigid body. So let us take an object. Let's take a rigid body. Okay, and let us say that we are finding the angular momentum about an axis. Now the treatment that we're going to follow is a very restricted treatment. We're going to find angular momentum about some very special axes. Okay, now in general, this system actually breaks down and we come up with some more complicated things. We're not going to worry about it. Okay, as far as we're concerned, we'll always be dealing with these very special axes, and we'll do everything with respect to those special axes. So in this case, we have an axis, say, going through some point of this object, and what we'll do is we'll take one particle of this object of, say, some mass mi, and it is moving in a circle, and let us say that its speed is v and its distance is r. And what we know is that the angular momentum for this ith particle, okay, will be equal to m times v, which is its momentum, multiplied by r, and it's just that's just called the rri. Okay, and I called it capital here, so it'll be times ri. Okay, and what we know is if it's moving in a circle, then v itself is ri omega. Okay, it is equal to Ri times omega times R. And I write omega and I do not write omega I because if you recall, okay, for each particle here, if it's purely rotating, each particle will end up having the same omega. Okay, so we can rewrite this as m times Ri square times omega. Okay, and this is for one particle. So when we find the moment of inertia for all the particles, okay, the total L total for this object will be equal to, say, m. I forgot to put an mi there. Some particle mass mi. So it will be equal to m1 r1 square times omega plus m2 r2 square times omega plus m capital N Rn square times omega. So when we sum all these up, okay, what we end up getting is summation of mi ri square multiplied by omega. Now if you recall, okay, this mi ri square, this product is simply the the moment of inertia of the object. Okay, and so L total is equal to I times omega. So we come up with a very useful expression which says that the total angular momentum L total, okay, L is equal to I times omega for an object. Okay, here L and omega are vectors, and I, we will treat I as a scalar simply because of our choice of axis, but in general I is not a scalar. It has it's actually a very complicated quantity. It's an involved quantity called the moment of inertia. Okay, moment of inertia, and I'm going to write this in a bracket, tensor. Okay, something that we will not talk about, but if you ever continue to do physics, you'll come across this, and I want you to remember this. Okay, this moment in your life where I give you this information. Okay, so we have L equals I times omega, and so from here we also we can obtain our next relation, which was, if you remember, dl by dt, okay, which is equal to I times d omega by dt, and d omega by dt is simply alpha, and dl by dt is simply torque. So we also can obtain this expression that torque is equal to I times alpha. Okay, so the angular momentum is simply I times omega. So if you know the moment of inertia, you could figure out the angular momentum. This is for any axis, it doesn't matter. As far as it, rather I shouldn't say it doesn't matter for any axis. But if you know the moment of inertia for an object about a particular axis, you can find the angular momentum for that axis. Okay, about that axis. Alright, so in the next video, what we'll do is we'll apply this to some simple situation.